We start off with the second year in review, this time on system-level ESD, and it will be given by Harald Gossner, who has been working on modeling and system-level ESD for a long time. We can consider him one of the founding fathers, considering his work in the Industry Council. I'll give the floor to Harald.
Thank you, Guido. Welcome to the year in review. Thanks for coming even at that early time and leaving your breakfast to get some food for thoughts. I hope I can provide this. You know, the tradition in the year in review is to go back a couple of 1, 2, 3, 4 years to see what has been published in the field, to share it with the community and make it available to you. And I did this now for the purpose of the system ESD or system level ESD publications. I looked into publications basically going back about 2015, so to collect a bigger bunch of material covering basically system level and IC protection codesign, discharge pulse models and models for I/O and TVS supporting this codesign approach, ultrafast discharges, the system and PCB analysis methodology like EM scanning, and other novel approaches in system-level testing to address real-world soft and hard fails. Actually, I have also selected a bit more the soft fails as a separate group. Sorry. Yep. And this is what I did to prepare for this year in review. I basically looked into the 73 papers coming over these years, stretching from 15 or ranging from 15 to more or less 18 probably. I haven't caught the last few months. Sorry for this. I know there are some more, but I think it's at least something you can catch up for a while when you look into these papers. I have tried also to give a bit of a statistical view. Where are preferences? Are there any developments? And are there any trends to be identified? So I split it into these 6 groups: actual codesign, modeling for codesign, ultrafast discharges, system PCB IC analysis method, soft fail analysis, and real world. So, I mean, what you can see is basically that there is, what I wanted to point out, that soft fail was pretty strongly represented here over the years in total. There's also a lot of ongoing activities in what's called SEED and other I/O and TVS modeling topics. Actually, there was a little bit of a peak in 15, probably due to that there were the white papers out and there were activities started also at the universities. I have to add that 2018, of course, didn't count, for example, the papers which will appear or have appeared in this conference. So to some extent, so it's a bit underrepresented. I would say probably this number would go up dramatically. What I've seen in the conference. So these are the 2 fields I have identified have some stick out of the others. I mean, we know for a long time that real-world events have some focus, but as I said, we have these analysis methods also developing. So gives you an idea what topics are predominantly addressed. The other statistics I did and data analysis was, where are these papers appearing? What are I call it the hotspots for this topic? And the good message is the Symposium is one of them. So we have, from these 73 papers, we have 22 at the Symposium. We see 23 I have found in the transaction of the EMC Society, and next to it there is the EMC Symposium, following with 11 publications in these years. The rest is basically split it. I mean, there is an Asian Pacific EMC conference, which still has a lot of contributions in this field, and the TDMR journal also has covered 3 times this topic in the 3-4 years. But I would say the readout is that we have, with the symposium, already a very good attraction of these papers. And when we focus on this kind of 3-4, you will grab most of the publications ongoing. So let me dig then into the, I call it the top stories. It's of course a kind of a subjective selection of papers, so don't blame me if I don't mention another one. I mean, most of them are very good, so I had to do some selection given the time frame here. So let me start with a paper provided by the group of Mingdu Kerr from Taiwan, titled "A System-Level ESD Protection for Automotive Electronics by Co-Design of TVS and CAN Transceiver Chips." It's basically applying the seed idea without a lot of modeling. It's just comparing the IV characteristics, this TLP characteristics, and matching them, and so they could successfully realize an ESD protection for the CAN transceiver, as shown in this TDMR paper. It's somehow similar what we have seen also in this conference earlier, has some analogy to the USB interface improvement as presented by Peng-Yu Wei earlier this week. This is basically a work, what I wanted to mention here also, Peng-Yu Wei. It was at the conference, you might have seen it. It addresses the IC level co-design aspects, and a previous paper has come out already at the IRPS, and this is what I'm highlighting here, which was more digging into the actual configuration and the topology of the USB, so even combining then topological aspects and SPICE simulation led to a very successful prediction of what will happen during a discharge. So next is a paper given by Elise group called "Practical Methodology for Extraction of Seed Models." Actually, it was given here at the conference, so I tried to limit somehow the papers which were given here, because you might know. But this was pretty interesting because it was an early application of the seed model, actually a full transient analysis, and you see here the setup for this interface and doing the comparison with and without the TVS diode, showing also the impact of T-cap caps as well as powering. So it's, I think, a very interesting early paper on this seed modeling topic. There's another paper, a series of papers actually out, basically from the group in Toulouse. Fabrice is mainly heading this activity, Fabrice Cagnier. So this paper specifically was titled "Hierarchical Modeling Approach for System-Level ESD Analysis from Hard to Functional Fail" at the Asian Pacific Symposium on electromagnetic compatibility. It's basically promoting a state model, even for snapback devices, and it has shown to successfully reproduce the predictions regarding the actual measurements in an HMM setup. There is a series, and this kind of work has now gone into a recommendation of a standard. So there are 2 bodies working on standard for seed I/O and TVS models. This is here in the organization, the working group 26, which is actually led by Fabrice. And there is an upcoming ISC standard. That's in the TC47 group. It's currently in industry review, so the document is ISC. Now I try to remember 62433-6, which is defining now the a kind of a framework for a system-level model for both PCB components as well as I/O. Next, I want to highlight a paper also going back to 2015 by the group of David Pomeranke, by T. Lee and others, system-level modeling for transient electronic discharge simulation. Basically, what they did is to investigate this kind of, let's call it an HMM setup, and looking into the aspect of the return path. This is a very important topic. I mean, in the simple seat, we just consider often the VDD, VSS as ideal things. They are not. And this gives an idea how big the influence is, even in a very simple setup. What is the aspect, what is the influence of the cap and the inductor, for example, in the setup. These kind of checks or tests will go on now also in the round robin, which is currently performed by the working group 26. So coming now to another paper, just to mention, which fits in this row, just for to cover it comprehensively. That's by Ben Orr. It's actually given in this conference in 16, where he pointed out for a 40 nanometer CMOS I/O technology. He looked into the aspects of powered and unpowered I/O models, and it was clearly shown that the 3-terminal model is needed, and that there is a certain dependency of the fail threshold depending on the driver state, which makes it a bit more complex to model this on the I/O side. Next is a paper also given by the group or provided by the group of Fabrice Quenier. Fabrice Escudi is, I think, a PhD student of him, where he investigated the transient behavior and the limitation of a quasi-static model for an I/O in this case. The problem was that this was a high voltage device, and he showed that neglecting transient effects led to much too optimistic prediction of the behavior under high current. So the conclusion is that there's need to model dynamic turn-on of high voltage I/Os with a snapback behavior. So that's very specific for this high voltage I/Os at that point. Switching gear basically to ultrafast discharge. I think this is a very interesting topic. We have also seen some papers during the conference here. It started with some more recent investigations. Of course, they're older work, but in the time frame I was looking at, there was this paper by Henry Wolf and Horst Gieser on secondary discharge, a potential risk during system-level ESD testing, given actually here at the symposium. Basically, they investigated, they did a very high frequency resolution, very accurate time analysis of the discharge with an extremely high broadband scope at that time. So they were charging up a floating piece of a little system or a little module, and this created then a discharge to the ground plane. Of course, there is no limiting resistor, we all know this, so that can be a very hard discharge, very fast, very high in amplitude. So what they were showing is that within, it can be like half a nanosecond and less, with incredible peak currents of several hundred amps here. Typically, as this does not hit any sensitive part of the circuit, it's not an immediate threat to a hard fail, but you generate a huge electromagnetic pulse, so to say, which enters into the system and typically leads to mole function. In some cases, can even lead to fails due to the enormous amplitude of this EM pulse. The other investigation on ultrafast discharges was done by Pasi Tamminen and Rita and Rick. on charge device ESD threads with high-speed RF interfaces. Actually, sorry, this is wrong, a typo, 2017, of course. So he investigated basically a connector, a charged connector placed on a board which is already partially assembled, and depending on the size of the RF IC in this case, and this very well-designed high-speed traces, you could get significant discharge. And what was really striking is that you saw rise times with less than 30 picoseconds coming up. While we are talking, usually when we do our CDM testing, we think of more 100 picosecond, something like this. So another contribution to the aspect of ultrafast discharges was given by David's group, by T.C. Lee, a full-wave simulation of system-level disruption during secondary ESD events in a smartphone. That was more less focused on the waveform, let's say, but it was more focused on the actual impact it has. So the interesting thing and to learn from is that they carried out the transient simulation, co-simulation of a 3D EM and the circuit. So they could really reproduce the coupling of the secondary discharge into the victim pin, which is a pretty interesting technique to do a full failure analysis and understanding of such a discharge and the impact on the system. Next topic I want to cover is the system PCB IC analysis methodology. Here, the aspect in this paper given by the Samsung group, and I'm not mistaken, and Park and colleagues, it was presented at the AP-EMC, measurement and modeling of system-level ESD noise voltages in a real mobile product. So they took an actual product and forced or discharged into the system in one corner of the board, basically one connector, and had obviously the grounding strap attached to another part at the opposite corner of the board, so drawing all this current along this line, causing then a disturbance of the supply network. And you see here some measurements and simulations of the actual fluctuations in the supply voltage, the deltas. And you see you have something in the several 10 millivolts in this system, which might give you an idea how critical it could be. It's addressing, of course, just soft fails here. Another very interesting work which gives us real insight into what happens during the ESD discharge regarding supply noise and impact on how the root cause of the fail is actually when you look into ESD discharges causing soft fails, was delivered by Nick Thompson and Elise Rosenbaum's group, on-chip monitors of supply noise generated by system-level ESD, actually given in this conference. They designed variants of sensors to detect actually very sensitively the voltage overshoot or undershoot during a system ESD, and to allow to read it out. So the good thing is in this case you can use it for the PCB as it is. It's something you can really implement and use the regular interfaces to read out this information. And it's of course important aspect here is that you place it at various nodes. I mean, this is the critical aspect, while when we look on the aspect of hard fails, we're focusing on the I/O. When you need to understand soft fails, typically you have to look into the power distribution network of the whole chip. So you need to have to get a full understanding and control, you would need to place such kind of sensors at several places, at many places, yeah, probably in the hundreds. So it's important to understand or to optimize here the size and also to think about how to read it out. There's now more work going on how these kind of sensors can be optimized. And the next work is coming from is coming from David Pomeranke's group, Hossein Bey and co-authors, a study on correlation between near-field EMI scanning and ESD susceptibility of ICs, presented at the EMC conference in 2017. So the approach was to use an EM scanning system and let the system run with different load conditions. So here is a picture just for the standby. They had some YouTube running, other whatever activities started, and took monitored the activity profile by having a small electromagnetic head. Yeah. So that's what was the starting point, and then they run the system again, but this time a head was used which injected interference. So it was a TLP pulse applied to this EM head, and then you monitored the regions of susceptibility. And what they discovered is that the regions match very well. So basically, the regions of high activity were also the regions of high sensitivity. Yeah? So, and they could correlate this for the different load conditions, and they did it for different frequency regimes, that there is a high probability when you understand where are your high activity regions, you already know where there's the highest sensitivity for a local or to be susceptible to an EM signal here. Yeah. So another work I wanted to mention here is a continuation of the on-chip detector activities I mentioned before from Elise group. There's another activity at David Pomeranke's group by Abhishek Patnaik. It's this paper is titled "A Transient Event Sensor for Efficient System-Level ESD Testing." It has been presented at the Transactions of Electromagnetic Compatibility. He has presented a almost similar paper, very similar paper here at the conference a year ago. So the main purpose of the paper is to show a new on-chip detector, which has actually a pulse width dependency. So this makes a difference to the previous paper from 2015 from Nick, which basically monitored just the level. In this case, the sensor was designed in a way that actually pulse widths of the interference on the VDD or the noise of the VDD could be detected as well. So it's a further step towards understanding what is happening during a system ESD actually on the chip when you finally see some soft fails. Another analysis method I wanted to mention, I think it has been discussed several times already, is the so-called directional injection developed by Ben Orr. Was presented at the conference here in the papers, a passive coupling circuit for injecting TLP-like stress pulses into only one end of a driver-receiver system, addressing the problem. If you want to investigate soft fail behavior, you have to have a system running, and so to inject a certain stress, you have to attach it while the system is running, so you have to make sure that just contacting it does not already cause a malfunction, so it has to be low capacitive. And second is when you inject then, you don't know whether it's going left or right. So if you want just to investigate the susceptibility of one of the interfaces, one of the pins, you have a problem, and this problem was tackled basically by this injection head now, canceling out the unwanted injection direction. So it's a very valuable tool for testing system susceptibility regarding soft fails. Another topic I just wanted to mention came out more recently by Sebastian Koch, identification of soft fail mechanism triggered by ESD stress on a powered 3.0 interface. That was actually a work focusing on, there was an observation on the system side, so basically the USB showed various failure signatures during a pulse. So basically there was interference, then there was ISC pulsing, but also targeted TLP stressing. So part of the TLP stress was, for example, applied to the RX, and actually at the TX it showed up as a massive interference or massive noise, which caused then the problem that the connection was not anymore stable. It has either to be enumerated or it had to be recovered. Yeah. So there was a little bit, more analysis done, and this is, I think, the more interesting part, because one could check some internal nodes. So, for example, there was an LDO debug out. So what one saw is during the injection of the TLP pulse, this LDO signal went dramatically up. So you had a lot of overshoot on the internal line of the LDO. And in this case, the LDO was coupled both to the receiving network as well as to the transceiving network, which is not a good idea. And by this, you could couple a lot of noise into the TX, and you finally, caused the soft fail behavior. So it's a kind of, the lucky situation was that you could really look into by having some test pins. The advantage of the sensors are you can really sense it somewhere where you don't have a actual actual readout possibility. Yeah? So strongly promoting the sensors direct readout possibility is very limited. It's also about speed, there are many factors limiting this. Yeah. So another topic on the soft fail aspect is presented by O.H. Isadi and the group of Pomeranki at the International Symposium on Electromagnetic Compatibility this year, called the Systematic Analysis of ESD-Induced Soft Fails as a Function of Operating Conditions. Basically, the learning is that depending on the load and the existence or non-existence of decaps influences strongly the ESD susceptibility. What you can guess, because basically if your VDD is not stable, if you draw a lot of current already and you have less caps compensating fast changes in your system, then you get more sensitive to ESD discharges when they create supply noise. Yeah. So also of course, there's the finding that when you have higher voltages, let's say you go up with your supply voltage, usually you decrease the ESD susceptibility, but of course this is counterproductive regarding the power consumption. So we see that there is also, I think this was also part of the discussion yesterday we had in the working group, in the workshop, that just the low power requirements, lowering the VDD automatically also increases our ESD soft fail susceptibility. So I want to share also some aspects of system level testing. That was the paper which actually got the Best Paper Award this year. I want to highlight Wolfgang's contribution here. Risk assessment of cable discharge. So the concept was to build up a real-world discharge scenario where basically the cable was charged up and there was a spring-like mechanism so that this connector could slide into, or the plug could slide into the connector here, and causing then the discharge and the discharge waveforms under the various conditions of the charging, depending on the charging of the cable and the location of the charge in the cable. You could see very different, let's say, discharge waveforms, and some of them are really concerning, but because it's really bringing us up to several amps. Some of them, which are extreme, can be several 10 amps, but I would say that a couple of amps could be one realistic scenario where you have really, for a good cable, and relevant cable discharge. So the next approach of a system-level testing and a real-world testing I want to mention is the paper given by Kohani and the Pomeranke group on evaluating characteristics of electrostatic discharge events in wearable medical devices, comparison with the ISC 61-1000-4-2 standard given at the EMC conference. What they actually saw they did this kind of a configuration of a patient lying on a bed, let's say, or in a surgery environment, and having then opportunity to discharge, for example, to some devices nearby. Yeah. And what they discovered is that actually they saw a pretty massive currents, which are much, much higher than the ISC predicts. I mean, if you think of the 10 kV, the peak current would be around about 35 amps. The second peak current probably around the 20 amp peak, but they discovered some currents which are really, really, really high. Depending, of course, on the position of the discharger. I mean, assuming that there's something metallic attached to the body, so there might be more severe conditions one has to look into beyond the standard targets for ISC testing. Finally, I want to mention one paper of a kind of playful aspect. It's by S. Young and Pomeranke's group. It's called Non-Contact Human Body Voltage Measurement Using Microsoft Kinect and Field Mill for ESD application. Presented at the EMC conference this year. So the approach was basically using the Microsoft Kinect station to locate the positions of the body and the arms and legs, etc., relatively to the environment, and start then a calculation of the E field and voltage, so that it means at the end of the day you can get actual distant measurement of a human body charging without getting near to him and or the person and changing the condition. Here you can do it by an MS Connect. I found it a very interesting way of using this device. I think with this I would close here this short presentation, and I want to mention that the references, the list of references will be added to the slide set. I think the slide set will be provided after the conference. The little thing you have to do, you have to fill out this questionnaire. So this is what ESDA is requesting, to get your feedback for the conference, to improve the conference. So, and in return you will get the slides and presentations, and this will be added. Thank you very much.
Thank you very much, Harald, for this very interesting overview. There is still time for some questions. Or let me start off with a question while you're still considering your question. From your overview, I have the impression that there's a lot of focus on soft failures. And that makes me wonder whether we will ever be able to get the sort of model for soft failures that works equally well as seeds for hard failures. What's your opinion on this?
I mean, the reason why we get papers, I mean, and most of the papers are, the majority of the papers in this field are from academia. It's a challenging problem. Yeah. So obviously you're in a research phase, and this is clearly where you get good new technical paper, a lot of technical papers. So we are on the way. It's hard for me to predict. I see it as a good, direction now and a good move that there are more and more papers addressing this. And what I could think of is that we get, at least for the supply noise, some idea. So that you have, this is also part of the simulation, a regular simulation chip designers do. What is the margin for your supply noise? So having there a better insight and correlation between the external ISC pulse, that would be a good step forward. And here I see a possibility to really get a kind of a soft fail seed model at some point.
There's one question.
Jeff Donahue, Pragma Design. So these are all great and continuing to get better on instrumentation for ESD events, either on chip, on board detectors. But as an aside, and this is not necessarily directed to ESD forum, but how do we as an industry take all of this material and push it back into, for example, USB 3's notoriously poor response to ESD noise, which we've characterized well through here, that it knocks out super speed and reverts back to terrible training and you know, Dr. Gossner, do you know anybody at Intel who might, for example, take the industry's knowledge here on ESD and push it back into the protocol and make it more robust from a dynamic perspective?
Yeah. Thanks, Jeff. Of course, that would be a great step. I mean, obviously, you start with learning. I mean, you have to correlate. I mean, this kind of waveforms and noise observations. Yeah? You have to find the actual problem, root cause in the circuit. Like I explained in this one case, was the LDO was not properly designed and this was not properly separated. So this is a learning you would drive into your own organization because it makes your device more robust. Yeah? So I think that's a given. However, if there is not a criterion, this is what you're probably also pointing to, that we are measuring this as a standard, then you might have mixed quality in the field. Yeah? So that is what I would consider as a potential interaction to the USB community, that if we can call out a kind of an qualification criterion, they might then need to react on. But I think we have to provide something up front. Otherwise, it's just anecdotal or just observations, and to say, okay, that's a bad design.
Well, I mean, yes, I realize you could make a physical system more robust for a given protocol, but I'm talking about the fact that 50 millivolts of noise for 10 nanoseconds will de-link the thing and make it revert back to USB 2.0, and that's a protocol problem. That's a design of the interface problem. That's not an implementation issue. I mean, you could band-aid it to make it fix it work, but it really should be something that the protocol designers who probably don't consider ESD as a soft upset, that's not part of the development process, should bring that back in and say, well, we really need to make it not completely die because of that. It should recover in a nice class 1 way.
It's only so much they can do. I mean, if you lose
quit
packages,
defending
they can
them.
resend, or if you lose connection, re-enumerate. One thing actually, and here you're completely right, is if it steps back to USB 2, if this kind of failure mechanism occurs, that's of course something you can cover in the protocol side. Yeah. That's the one where I would say that this we should drive more urgently, let's say. Absolutely. I mean, it's typically for simple application, like when we do our download of our files, it does not cause a problem. But when it's in a system where we rely on the speed that the data are transferred from A to B, and it's wired, and it's not plugged out and in for more often, it's really can become a concern for the system. Yeah.
For the benefit of the discussion, like a server farm that has USB 3 drives or something out there, over time, as they get events, they just the whole data rate for everything just falls down, and it degrades over time, and that's just not really acceptable. I mean, that's
no, but this is a difference. Just to make clear, I mean,
take it to
the problem. Oh, we can discuss about this later.
All right.
Let's take the discussion offline because we're running out of time a little bit. Let's thank Harald Gossner once more for his excellent presentation. Now we will take a short break, and we will start back at 8:50.